Welcome to qnawire.
Hi everyone, so what we have here is air that's initially at 200 kPa, 100 degrees Celsius, and is flowing at a speed of 250 meters per second. And then we also have helium, which is also at 200 kPa, 40 degrees Celsius, and going at 300 meters per second. What we're asked to solve for is T star, P star, and rho star for both A and B. So for both of these gases at these conditions specified. And the way that we're going to be doing this is by first solving for the stagnation properties of the gas, and then using our isentropic flow relations to solve for T star, P star, and rho star. So let's go ahead and get started. So first we're going to do it for air, and we know from the gas table that R is equal to 287 joules per kilogram Kelvin. We know that K is equal to 1.4, and that's also something as gamma. And we know that Cp is equal to 1005 joules per kilogram Kelvin. So first, what we need to do to find the critical properties of the gas is we need to find the stagnation properties. And the way that we can do this is go ahead and define our user equation for stagnation temperature. We know that stagnation temperature T0 is equal to T plus V squared over Cp. And by plugging in the quantities that we have for air, we see that this is equal to 404.1 Kelvin. Next, we're going to do the same thing and solve for the stagnation pressure. So we know that P0 is equal to P times T0 over T to raise to the K over K minus 1. And this is an isentropic flow relation, and what this gives us is a stagnation pressure equal to 264.7 kPa. And next, what we're going to do is solve for the stagnation density of air. So we can say that rho 0 is equal to P0 over RT0, and this is just using ideal gas law. And this gives us a rho 0 equal to 2.282 kilograms per cubic meter. Next, what we need to do is we can go ahead and solve for the critical properties of air. So we know that T star is equal to T0 over 2 times 2 over K plus 1, and this gives us 336.75 Kelvin. We know that P star is equal to P0 times 2 over K plus 1 raised to the K over K minus 1, and this is equal to 140 kPa. And finally, we can just use ideal gas law, or we can actually go ahead and solve for rho star using, again, the isentropic flow equations. And this is equal to 2 over K plus 1 raised to the 1 over K minus 1. And this gives us 1.45 kilograms per cubic meter. Now, these are the critical properties of air, so that these are the answers for part A. Next, we're going to do the same thing, but do this for the helium in part B. So for helium, we know that R is equal to 2076.9 joules per kilogram Kelvin. We know that K is gamma is equal 1.667, and that Cp is equal to 5,192 joules per kilogram Kelvin. What we're going to do here is we're going to solve for these stagnation properties. We know that T0 is equal to T plus V squared over 2Cp. And for the conditions that were given to us for helium, we can plug in the values that we have on the right side, and we see that T0 is equal to 321.67 Kelvin. Next, we can find stagnation pressure, and by using the isentropic laws, we can say that this is equal to P times T0 over T raised to the K over K minus 1. And this gives us 214.13 kPa. Lastly, we can find the stagnation density, and we can say that this is rho times T0 over T raised to the 1 over K minus 1. And this gives us 0.321 kilograms per cubic meter. Now, these are all our stagnation properties, and we can use these to solve for the critical properties. So we can say that T star is equal to T0 times 2 over K plus 1, giving us 241.22 Kelvin. P star is equal to P0 times 2 over K plus 1, all raised to the k over k minus 1, and that's equal to 104.3 kPa. And we can say that rho star is equal to rho 0 times 2 over k plus 1 raised to the 1 over k minus 1, and this is equal to 0.2085 kilogram per cubic meter. And these are our final answers and critical properties for helium at the specified flow conditions.